Good morning, everyone. Good morning, everyone. My name is Erickson. I'm from MPQ, Max Planck Institute for Quantum Optics. So I think quantum optics person shouldn't be talking about algebraic stuff, I guess, but I will try anyway. So this is basically something that I've been trying to learn for a long while, and it's very difficult because I don't have background in functional analysis. But I realized that one of the great things about functional analysis is that you can black box most of it and only deal with them when it is important, when you really need it. So if you are trying to prove theorems for your own work, please watch out for the functional analytic stuff. But the beauty of this subject is that you don't really have to pay attention to this when you just start to figure out like what they are useful for. So I'm going to try to do most of this. And the first of all, I'm going to mention that there are many reasons why you can study operator algebras in general. But I would justify it based on my own experience, which is necessarily biased, okay, and it's probably like a measure zero. So I'm not qualified to justify all of them, but one of them is very natural, which is from the perspective of quantum field theory. I don't know how many people here work on quantum field theory in the relativistic regime, but for people in the relativity, this is extremely relevant.
Erickson, I think we lost you for a second. You're back.
Okay, so unfortunately, the Wi-Fi here is not exactly the best. For some reason, EduRoam is not very good.
I think there was a rhetorical question about whether we work on quantum field theory, and nobody said anything for now, but we can discuss later as well. And then you wanted to say what you will focus on, but that we didn't hear anymore.
Okay, so all I'm saying is that I'm going to focus on mostly the algebraic part, and the functional analytic part you should assume that it's going to be hidden somewhere. But you should notice that a lot of the functional analytic work is at the background. Okay, now the way I would justify it is the follow. Before that, I will just mention some references that I will use. I will actually add some of the reference here later when I go to the next few sessions. So if you want the slides for whatever reason, you can ask me. But otherwise, this is the first three that I use. The first one is Introduction by Algebraic TFT by Chris Fuster and Kasia Reisner. They are one of the few people who works extensively on algebraic quantum field theory. And then there's also Stefan Hollands and Cole Sanders on their work by entanglement measures of quantum field theory. And then there's the von Neumann algebra analysis for entropies by Mario Berta and others. I will add a few more later. But first of all, I want to mention that in finite dimensional quantum mechanics, one way to view the bipartite system is to simply to put a partition on the Hilbert space. Okay, so for example, if you have spins, you can just split the Hilbert space the way you want it, and oftentimes you want to split it also according to how they appear in real space. So in this case, you have a spin chain, you can divide them in real space by half, and then you count the Hilbert space of, say, Alice or Bob by whichever they're holding. Of course, if you partition by Hilbert space, you don't have to follow the geometrical partitioning, but normally these go hand in hand. But the problem is that if you will see the problem later when you realize that this also means that if Alice wants to do something only on her subsystem, then it corresponds to saying that she can her algebra of observables is essentially like a tensor product of all the possible bounded operators on Alice's side and does nothing on Bob's side. And similarly on Bob, it's also the other way around. So this is one way to think about local algebras that each observer or subsystem can do. And of course, if you just think of it in this way, then this is also the statement that local algebras commute. So if the statement that Alice only does something on her subsystem and nothing on Bob, and vice versa, is the same thing as saying that whatever they can do on their own must commute with each other. Okay, of course, if you include time evolution and whatnot, then there's a complication because Alice's operators can spread, but we are not talking about that right now. Okay, but now if you just jump a little bit to scalar field theory, which I hope many of us have seen a form of it in electromagnetism. At least you can think of scalar field as just electromagnetism without the vector part. You have a field that satisfies the wave equation. The solution of the wave equation can be found using Fourier transform, and canonical quantization amounts to putting hats on the Fourier coefficients. That's one cheap way of thinking about quantum field theory, okay? And you realize that a quantum field theory can be regarded as essentially a continuum of harmonic oscillators with kind of like a spatial coordinates labeling it. And you can see why it is the same as harmonic oscillators, because the A and A daggers obey exactly the same thing. And you can even check that the Hamiltonian is sort of the same thing. But the moral of the story is that now we want to consider a different quantum mechanical system, which is a relativistic quantum field given by the following canonical commutation relation. Now, why do I want to bring this up? The reason is because that even though structurally from the Hilbert space perspective, it has all the good features of a harmonic oscillator. For example, the Fock vacuum is exactly what you would expect. Now you can ask yourself, in this case, what would be the subsystem of observers for the scalar field? And it turns out that it is a little bit trickier compared to, say, a spin system of a harmonic, or let's say a harmonic chain. The reason is because if you now take the field on a space-time and you try to do a bipartition on, say, the left and the right part of, say, constant time surfaces, this doesn't actually work. Actually, you can. It is a deep result of algebraic quantum field theory that you cannot do a Hilbert space factorization on the left and the right part. So this has many incarnations. So, for example, if let's say you have ever taken the reduced state of a quantum field on just the right part, you realize that the von Neumann entropy diverges. Okay, this is actually the same thing as saying that there is no Hilbert space factorization. Okay, however, you can still define subsystem in terms of operations that are allowed by each observer. So for example, you can still perfectly define that the local algebras by Alice and Bob are exactly restricted on the left and the right wedges of the spacetime. And they commute by definition because of the light cone. So you see that the operators on each wedges, they are space-like separated. Okay. But the fact that the Hilbert space doesn't factorize, it means that you cannot actually think of the local algebras of Alice or Bob as basically a tensor product of bounded operators on the left side or the right side, tensor identity on the other side. So this is actually sort of like related to the separation of the commuting framework and the tensor product framework in the Cyril-Son's problem. But for our purposes, it's really much simpler than that. It is just a statement that if you don't have a Hilbert space factorization, you cannot naively think of local algebras as simply a tensor product of operators. Okay. And furthermore, classically, we think of observers as kind of like some point like object moving along some trajectory, for example, right? For example, I have an accelerating observer. Now, how would you think about operations that this accelerating observer can do? Well, you would say that, oh, this observer moves along some trajectory, so they can only operate along this trajectory. But it turns out that if you ask yourself what kind of operations on the field that this observer can do, it actually turns out to be the entire right wedges, and this is completely fixed by causality. Okay, so this is just a statement because the thing is that the scalar field has time evolution, so it really affects what kind of operations that these observers share.
Can you say again what's the name of this?
The name of what?
You said this is called something.
This is basically related to causality. It has to do with the fact that okay, I might not shade this correctly. Actually, I think I also need to shade the future light cone. But basically, you see that if let's say accelerating observer acts on some point along the red line, right? Everything that is in the future light cone of that point is going to be affected by is going to be affected, which means that the local algebras of observables is really not just localized on the red line, but anything on the future light cone of whatever is on the red line. So it's really kind of like half the space-time, so to speak. So I actually kind of shade this the wrong color, but the point is that once you take into account the dynamics of the theory, just because you're localized on some trajectory doesn't mean that your local algebras are strictly localized on that trajectory. But the point is that this is completely fixed by the theory. Okay, but to summarize, if you think about QFT, right, the operator algebraic formulation is already simply preferred only within these few slides, just because even though you don't have Hilbert space factorization, you can still think of local observer subsystems and what kind of operations that each person can do. Okay, so this also makes it clear that when we think about, say, okay, this might be getting ahead of myself, but when you think about entanglement, you really have to think about from the perspective of algebras and the states. And this might appear, okay, I'm bringing the Rees-Leader theorem here because it appears in the emails, that there's this statement that if you are given a state of a quantum field theory, then local algebra action on the state is actually dense in H. So it means that the ground state of a quantum field is in a way kind of entangled, because doing local operations can approximate any state in the Hilbert space. But the point is that this is a very natural language in the operator in a operator algebra context, and at least for the next few sessions, I'm not going to talk.
So H is now the global manifold, or maybe we lost Erickson again.
This convinces you that there's the operator algebra.
Erickson, I think we lost you. I thought you took a break.
No, sorry. Yeah.
I think it was like maybe 15 seconds glitch. But can you say the theorem is extending a small tiny patch into the entire space M? Or so it's dense on some larger space-time regions beyond O, or how is it?
No. So if, let's say, I take a quantum field theory which has the quantum field theory is associated to some Hilbert space, right? Which in this case can be regarded as a Fock space, for example, right? The idea is that even if you restrict the local algebra to be associated to arbitrarily small region of space-time, you can actually approximate any state in the Hilbert space. Of course, it's a different story from saying whether those things are implementable. Okay, so there's this joke by Edward Wheaton or maybe some other people that say that you can create the moon by doing local operations on the lab. And of course, there is an operator that can do the job, but that operator is not unitary. But the point is that the fact that local algebras can already approximate any state in the full Hilbert space is just a statement that the quantum field theory, any state in quantum field theory, especially the ground state, is in general a very entangled state in a particular sense. But of course, the problem is that there is no good measure of entanglement in this case.
So
this to me,
I think you said it now. You said full Hilbert space. So the mathcal H that you have in the outlined equation is the full Hilbert space on this on entire M. Yes.
Yes, that's right.
Okay, thank you.
and
That's right.
this to me has a very similar ring to the fact that if you have an analytic function on the complex plane, then having it defined on just some open interval, any of any size, fixes, like, determines its behavior everywhere. Is it related to that at all?
That's a very good question. So I'm not 100% familiar with this, but I believe what you said is correct, because to prove this, you actually have to use the fact that at least in flat spacetime, these states are what we call analytic states. And so it has a good limit in the complex plane, so to speak. Because the thing is, one way to think about it is that the correlation functions of a quantum field theory is actually some boundary value of some complex functions. So what you say definitely is related. But this is also the reason why in this Rees-Leader theorem does not easily go through in curved spacetime. So for example, if you want to prove quantum field theory for the ones that you use for Hawking radiation, right? This proof is much harder because the complex analytic part doesn't easily generalize to curved spacetime. Is that fine?
Yeah, interesting. Thank you.
Yeah, but Edward Wheaton and I think Borchers might have proven something along that direction. Okay, I think in the interest of time, I will try to move a little bit, and hopefully some questions we'll just make sure that the time works out. But I think I will go slowly, and the hope is basically for the next at least 2 to 3 sessions, I would like to introduce basic framework of C-star algebra with some simple examples, its application to quantum information theory, or at least it gives you a nice reformulation of what you are used to. And in the long-term goal, I will try to mention a little bit about quantum field theory. Okay. Now, this part is going to be somewhat mathematical, but I hope it is sort of well motivated enough that you can sort of absorb it along the way. And the first is to mention that actually at the back of our minds, when we think of observables, we actually have some sort of associative algebra. It is basically an algebra with the associative property that we usually think about matrices. Okay. So in the next few slides, please think of it using matrices if you like for intuition. So a complex vector space is an associative algebra if it has the associative properties, that means consistent with the brackets. And also we say that it is unital if it contains the identity. And the technical language of C-star algebra, it is just such an algebra with an involution map. That means something that applies twice gets back itself. It has the property that AB star is B star A star, and it respects all the linearity and conjugate complex conjugation. So you realize that if you think of it as matrices, right, the star algebra is basically just an algebra of matrices equipped with Hermitian conjugate. But I will stick with the word star simply because people don't call it like a dagger algebra. Now, you can also equip something with a vector space with a norm, right? So you say that it is a norm algebra if it has a norm, and this norm automatically defines a topology, because once you have a norm, you can define convergence of some say elements in the algebra. And an algebra is a Banach star algebra if it is a complete norm star algebra with an extra property that the norm of the Hermitian conjugate should be the same as the operator itself. Complete means you include all the limit points of any sequences in the algebra. Okay, and you realize that in 2 slides, I'm already trying to define what a C-star algebra is. Basically, C-star algebra is a Banach star algebra with a very strong C-star property, which is that the norm of the positive operator formed by the A dagger A is basically the square. Okay, and we'll always assume that the C-star algebra is unital. The reason has to do with the fact that if it is not unital, you can always construct an extension that is unital and you just work with those. Okay, so far so good. Is it too fast? Okay, if not, I will continue, but please stop me if there is anything.
It's okay if it's, you know, I mean, it's not too fast unless like details from here are really important later, right?
Yeah, so the point of this condensed version is that these are all the essential features that you can just absorb if you have seen a vector space before. Okay, I'm skipping a few things, but you can always ask me later, or I could give you the references. But what I'm trying to do is that so long as you know what a multiplication is, you know what a norm is, and you know what a vector space is, in general, these things should be more or less kind of like consistent in your head. Okay, of course, in infinite dimensions, these are all very tricky because the Hermitian conjugate has a different domain and whatnot. But I hope sticking to matrices in your head might really help. Okay, so I will give you 2 examples. The examples that one of which is maybe familiar, the other one may not. If you take some bounded continuous function on the real line, okay. So bounded just means it has a maximum and minimum. Then it forms a commutative C-star algebra with polynoise multiplication. And the norm, you can just use the supremum norm. That means you take a modulus and evaluate what's the least upper bound. And the complex conjugation is the Hermitian adjoint. Okay, this is not so common for physics, but is a nice, cute example. But otherwise, our finite dimensional quantum mechanics is essentially giving you for free that The unital C-star algebra easily comes from the n by n matrices with complex entries. And the operator norm, you can just use the standard operator norm, which is the supremum of the norm of all states with unit length. And the Hermitian adjoint is just a standard Hermitian adjoint. So I hope you can at least use this second example to verify for yourself that actually we have been having C-star algebras on our table since our second year of undergrad. Okay, now, why is the Hilbert space example so important? The reason is because there is a theorem that shows that any C-star algebra is isomorphic to a norm-closed self-adjoint algebra of bounded operators acting on some Hilbert space. Okay, this might be a bit mouthful. Norm-closed, it just means that you include all the, I think you include all the limit points under the norm. And self-adjoint algebra, it just means that if A is inside the algebra, the A dagger is also inside the algebra. But the point here is that any C-star algebra is basically some subalgebras of bounded operators acting on some Hilbert space. Of course, I don't know which Hilbert space it is, but it's going to be the same picture. So once you have this picture, oftentimes you don't need to get away from this. And in mathematical community, this is usually called the concrete C-star algebras. That means I'm viewing a C-star algebra as a concrete realization as a bounded operators acting on some Hilbert space. Now there's a good, rich, very beautiful spectral theory of C-star algebras that generalizes the spectral decomposition and whatnot, but I'm not going to cover it here unless we really need it later. But today and the next few weeks, probably not. Okay, but the good thing is the concrete C-star algebras really lets you have a lot of the intuitions carried through with minor modifications. Okay, I wouldn't say minor, but a lot of times you can really think of it this way. Okay, now I'm gonna have one slide on representation theory. Okay, I think this is like in my life, I think I've never summarized representation theory in one slide. Basically, if I give you two C-star algebras, I can define a star homomorphism to be just a linear map between the two of them that respects all the algebraic structures. That means if they are linear, the map will send linear stuff to linear stuff. The Hermitian conjugate is going to be sent to the Hermitian conjugates, and the products is going to be sent to products. And this map, in the functional sense, is also bounded and continuous. By that, we mean that the norm of the image is the same as is at least bounded above by the object you start with. And it is not hard to see that actually the image of A1 under this map is going to be a C-star subalgebra of the A2. Okay, and a star representation is, we say that it is a representation if you give me one Hilbert space, a representation that sends A to the bounded operators is a star homomorphism. It is faithful if you get the whole thing. Does it make sense? So the point is that a representation is often a good way to realize linear objects in terms of objects we are very familiar with. So if you remember from linear algebra, actually this is exactly what we do with linear operators. We always think of linear operators as matrices, but that's basically a matrix representation of linear operators. Okay, so star homomorphism is basically exactly have the same spirit spiritually with additional properties that respect the star property. Now, if these things have to do with quantum mechanics at all, then we better have a state, right? So, but in the language of C-star algebra, an algebraic state or a state is really a continuous linear functional from the algebra to a complex number, with the property that it sends the positive operators have positive values and it evaluates to 1 to identity. But really, this is just a fancy way of saying that an algebraic state is something that takes in positive operators and spits out positive expectation values, and it is normalized to 1. Okay, so for example, if you try to define a state to be induced by the unit vector that we are familiar with, then you can you realize that this is really just the usual expectation values. Okay, but what is not so obvious is that you want to ask the opposite. can you always build a Hilbert space if I just give you this state defined abstractly in this way, and also an algebra that is defined in this way, right? This is not automatically obvious because the converse is kind of like something you can build directly. And this is exactly what the GNS construction gives you, which is the following theorem, that if I give you two objects, the algebra and also a state, then you can always construct a GNS triple. That by triple, I mean a Hilbert space, a representation, and also a cyclic vector, which the definition I give there. A cyclic vector is a vector so that if you act on the entire, if you evaluate it on all operators, you basically get the entire Hilbert space. So actually, this is related to the Ruiz-Leader theorem. But basically, the GNS theorem says that you can get these three objects such that it is a cyclic representation. The state evaluates to the expectation value of the cyclic vector, and then it is essentially unique up to unitary equivalence. Okay, and I don't know if it is obvious at this point, but this is just this is actually equivalent to the statement in quantum information theory that every state basically admits a purification. And I will give an example later that how this thing works out. Okay, so I will run through the sketch of the proof. The reason is because if you know how the proof works out, at least the algebraic part, you realize that actually this construction is kind of like a purification. And the way to do this is actually, you want to construct Hilbert space only from the algebra and omega, right? So that means somehow the algebra has to be made into a Hilbert space, and the omega gives you inner product. And first thing first, you should notice that for this to work out, you need to quotient out everything that has zero norm, right? Because a Hilbert space has an inner product that is only zero if it is a zero state. So the first thing you do is to construct the subalgebra that has zero norm. And then what you do is to quotient out this from the algebra so that the remaining elements are only zero norm if it is the zero vector. Okay, and you realize that this construction is actually very similar to equipping the Hilbert space with the Hilbert-Smith inner product, which is like the trace of A dagger B. And you realize that once you do this quotient space construction, basically every state is viewed as equivalence class of states up to the zero norm states. Okay, and then once you do this, you realize that now you want to construct the representation, and it turns out that the natural representation you get for this is the left representation. That means you declare that pi omega is basically the one you get by left multiplication. That means the action of A on the cat B is basically the multiplication, it results in a state that is A times B. Okay, and what would be the cyclic vector? The cyclic vector would be the equivalence class that is proportional to the that is equivalence classes of identity. Why is this cyclic? You can think of it like, because if you do left multiplication on identity, you basically just get cat A. But you can run through A to get the entire Hilbert space, because the Hilbert space is by definition all elements of the form cat A. Okay, and if you check that this is a cyclic, if you use the cyclic vector to evaluate expectation value, you realize that you indeed get the expectation. And finally, you can actually check, and I didn't prove this here, then there is a unitary that maps one to another.
Sorry, Erickson,
Yeah.
you dropped out half a minute ago saying something about the cyclic vector. But can you say again what's the cyclic property? Because if you have a group is cyclic if you have like a single matrix X and then you start taking powers. But here,
okay.
This is cyclic in the sense of applying the whole algebra or something, yeah?
Yes. So if I have an algebra, right, and I have a cyclic vector, essentially by running through the whole algebra acting on this state, I get everything.
Everything means that
in the full Hilbert space.
Yeah, so it's a cyclic representation of an algebra in the sense that you can create the full Hilbert space out of the cyclic vector.
That's right.
But it's a little bit different than the group cyclic stuff, yeah?
Yeah, the cyclic group you are thinking about is that is an abelian group with one generator that you can multiply, right? Spiritually, I think they are the same thing, but they are not defined for the same reason.
Okay, and then basically because it's the identity, then it's kind of trivial cyclic property, because it's like you're constructing everything because you're applying everything, so you
Yes.
have everything.
The thing is that once you define it by a left multiplication, then you realize that the cyclic vector identity is a cute way of getting the cyclic vector, right? Because you just multiply and run through the whole thing.
And can you say what's this definition of, because you now defined those cats of the equivalence class?
Yeah, so after you quotient, if you take an object, a group, an algebra, or a vector space, and you quotient it, then the elements of the quotient space are equivalence classes, right?
Yeah.
So now you define element of this quotient space as basically equivalence classes. So since I want to think of Hilbert spaces as having elements vectors, so I use cat of the, so in mathematics, the square bracket defines equivalence classes. But I use the word, I just add a cat just to make sure that it is a vector in the Hilbert space.
So basically, okay, that's what you meant with this Hilbert-Schmidt scalar product. So like you have an operation, some map on those algebraic elements, and then you show that it's a good inner product, and it's a vector space, so it becomes the Hilbert space, and then you just have this notation of cat of the box.
Exactly, and I actually do here that it is equivalence class up to zero norm states, in the sense that if you take another state, A plus B, but B is a zero norm state, right? Then it is essentially the same as the cat A, because you can evaluate everything and they get the same answer. But equivalence class, basically you're trying to take the same. So if you remember from the quotient space construction, that you basically regard several objects as being the same, right? And you just need to pick one representative.
Yeah. And basically on the equivalence class, it's non-degenerate, and then it becomes the Hilbert space, yeah?
Exactly. So that's really the clever part of the GNS construction.
Okay.
So
yes, Peter.
So one way to think about this is that you can do all this just saying, I'm going to work with a pre-Hilbert space, with a pre-inner product. And the only difference between a pre-inner product and an inner product is that the inner product, there's no zero mapping except from 0 to 0. So you can just work with this all just to say, well, if ever I get 0, then I have to check whether it's actually from 0 or whether it's from some other vector. And that works out effectively, but not for the case, you can't assume any Hilbert space proofs apply to if you work in that sort of thing, except you can always at some point say, and now I will take now I will work with just the equivalence classes. And so you effectively you can just not worry about this construction, I find. Anyway, carry on.
Yeah, thank you, Peter. So is someone else saying something?
Yeah. I just wanted to ask, does any C-star algebra have a cyclic representation?
Well, the GNS theorem guarantees this is true. You give me C-star algebra, I run through GNS, I get a cyclic representation for free.
Cool. Yeah, thanks.
Right, it is actually the statement, right? The fact that the GNS triple has a cyclic vector, it just means that you actually constructed the cyclic representation.
On the other hand,
sorry.
I'm not quite sure whether there's always a state for every C-star algebra that will give you a faithful representation anyway. Because you've obviously got the trivial representation, which just sends everything to 1.
Let's see.
I mean,
the trivial representation will not be the GNS representation, right?
Right. Well, no, it still gives you a GNS representation. It satisfies the axioms, for the requirements for it to be a state. So to zero, you have everything to zero. Then you get a perfectly good, completely trivial state and a completely trivial representation. But it still satisfies the four axioms, the four requirements for a state. Anyway, let's not worry about it. Sorry.
Yeah, I will have to check about it, but I think in general you can always run through this construction and get something. What's really not obvious is that the Hilbert space is separable. So that's the hard bit actually. Okay. Now I will just mention one last thing about the state, which is that of course in quantum information we know a state is pure or mixed, right? But the thing is, in an algebraic version, a state is pure if you cannot write it as a strict convex combination of two other states. And this might look a bit tricky because state kind of evaluate expectation values, right? But I should mention that this is actually closely related to the GNS representation in the sense that if a state is pure, if and only if the GNS representation is actually irreducible. And the way to think about this is that if it were reducible, right, then you can represent the state as a vector that looks like a direct sum. And you can then evaluate the expectation value like a block diagonal matrices acting on those stuff. So spiritually, this is exactly what happens. If it were pure, then you don't have a block diagonal decomposition of the same object. Okay, I'm not going to prove this, but most of the time, the proof goes along this line. And you have to prove that there is a projection into the correct invariant subspaces. But morally speaking, this is what happens. Okay, now just to stop and summarize a little bit, basically, one way to think of operator algebraic approach to studying quantum theory is really to think of everything in terms of the observable. So you are really working in the Heisenberg representation, and C-star algebra and its concrete realization is really something that you should think of as like a bounded operators acting on Hilbert space. And then the GNS theorem essentially gives you the Hilbert space representation. So the point is that you always get the Hilbert space constructions out of the operator algebraic formalism. So you don't really have to worry that the Hilbert space is lost somewhere. Now, the separability stuff really only matters when you do like infinite dimensional stuff, but in finite dimensions, this is essentially equivalent. And the way I will show you this, which is the last part of today's presentation, is just a short cute example. So let me take a qubit. Okay, it's a two-dimensional quantum system, and the algebra is going to be matrices that is 2 by 2 complex matrices, and a state is basically a map from 2 by 2 matrices to complex numbers. And you realize that in finite dimensions, actually, you can always associate such a state with a density matrix. And the way to do it is to realize that since an algebraic state spits out expectation values, it should exactly correspond to the trace of rho times A. Okay. Now, of course, somehow I sort of invoke the GNS representation somewhere, but we'll see. Okay. Now, before that, I'm going to introduce something that may be familiar if you are quantum information, if you work in quantum information for very long, or at least longer than I am, is the vectorization map. So if there is a map that sends matrices to tensor product of vectors, basically by taking a ket times a bra to a double ket. Okay, and by linearity, you can see that it sends arbitrary pure states to a state times its complex conjugation. Okay, and why is this important? The reason is because vectorization defines what I would say a canonical purification. Okay, it's not really canonical because it is basis dependent, but it's canonical purification in the sense of what John Watrous used to say in his classes. Okay, he says that if someone gives you a density matrix, in 5 seconds, give me a purification. And the answer is to just take a square root and vectorize it. Okay. So basically, you take the density matrix, do spectral decomposition, put all square roots on the eigenvalues, and just flip all the bras to kets. And there is a nice identity I should just mention here, because this identity is actually very useful, especially if you have seen tensor networks. It's basically that the vectorization of products of 3 matrices can be factorized into actions of tensor products. Now, The GNS theorem, I claim, is that in infinite dimensions, essentially, is just a purification by factorization. And one way to see this is to use one example that is very familiar to us. So consider a maximally mixed density matrix, which is identity over 2, and take the algebra, and you realize that if you run through the GNS representation, this is nothing but the cyclic vector up to some normalization. Because if you factorize the identity divided by square root 2, then you just get a Bell state. Okay, and you can check that for this Bell state, the zero norm subspace is actually trivial. Basically, the only operator, the only matrix that has zero norm under this evaluation under this cyclic vector is actually 0. Okay, and consequently, the Hilbert space construction under GNS is actually the full C4, which is just the factorization of the 2x2 matrices. Okay, and in fact, you can just easily check that this is a cyclic vector because the Hilbert space representation of the operator A is 2x2 matrix ABCD. If you factorize it, it's just a vector ABCD, but that's basically a full parameterization of the Hilbert space up to normalization. Right?
So the only difference is that when I have like a big C-star algebra, I might not have an array of numbers that I could just list, right? But this kind of equivalence class multiplication with the equivalence class of identity is kind of this, yeah?
Yeah, and if you try this for pure state, say rho equals to cat 0, right? Rho is cat 0 bra 0. You realize that there is zero norm subspace, which is the ones the ones that has 0 column on the second component, in which case you have to quotient out to get the Hilbert space, which is like C2. Okay, and cute enough, if you have ever checked vectorization map, right? It has the cute property that the Euclidean inner product of the vectorized vector is actually the same as the Hilbert-Smith inner product, but that's also exactly what you would expect from the GNS inner product. This is actually kind of like a hidden indication that the GNS construction is just vectorization. And you can also check that this representation is reducible because we claim that this is a mixed state, right? So it has to be reducible, but how do you see this? So the cute way of saying this is that for matrices, right, you can view the left representation as basically tensor product of A tensor identity. That means you think of it as a bipartition where A only acts on the left copy of the Hilbert space. So you think of C4 as C2 tensor C2, and you think of the left multiplication as A tensor identity, and you realize that when you add A tensor identity to the Bell state, you can actually completely rewrite this as a direct sum representation of A direct sum itself plus Bell state written as a direct sum of 0 and 1. So this representation is reducible because you can write it as a direct sum. If you run through this for pure states, it will not go through. So actually this way of thinking about pure state and mixed state is sort of inverted. So the way GNS representation think of mixed state is that anything that has Smith rank more than 1. So you might be used to the fact that we think of mixed state as something that is like how do I say it? Okay, I think one way to say it is that since GNS representation is a purification, then every state is a vector state. So it's not really useful to think of mixedness as density matrices, but once you think of it in this way, you realize that a mixed state is basically those whose vectorization has Smith rank more than 1. So that's one way of thinking about it. Okay, not the Smith rank, whose vectorization has direct sum of more than 1 component. And I think I should probably stop here because the next few slides is very technical, but I was thinking of reserving it for next time because I think we are out of time. It's already good 30 minutes.
Can you just explain again why the representation is reducible when you say it here? This is the representation induced by the maximally mixed state, yes?
Yes. So remember, the GNS theorem says that a state is pure if and only if the GNS representation is irreducible. So if your state is mixed, then the GNS
That's great.
representation is reducible.
Okay. And can you say what happens with this belt state? Why do we have the belt state there? The cyclic vector is the belt state. Okay.
Yes.
And now
So
you
if you
have
take a
split it
maximally,
into a direct sum. So you made it explicit in what sense it's reducible.
yes. So in the bell state case, this is very explicit. You can just do this by matrix multiplication. And it is cute exactly because in matrices, you can literally think of left representation can be embedded into the tensor product of identity. Basically, that's.
Yeah, and those direct sums you can also implement by tensoring the identity as well, yeah?
Exactly.
That's the trick, yeah. Okay. This is great, Erickson. I think let's maybe wrap up and maybe some questions, and otherwise I close the recording for today.
Yeah, yeah, my presentation is over. The next one is von Neumann algebras, but I'm going to reserve it for next time.
Yeah, and okay. Yeah, okay, great. Then thank you very much. This is amazing. Thank you.
Yeah, I hope that was cute, but
yeah, it's cute. It's very cute.